Oh, hello. I'm E from Apollo Scitech. First, a little bit about the company. Now we have been here in Delaware for 7 years. And before that, the company was in Georgia for 13 years. And we provide high quality scientific analyzers at affordable prices for the measurements of pCO2, of CO2 parameters, including dissolved inorganic carbon analyzer, stable isotope of DIC, seawater total alkalinity titration system, underway pCO2 monitoring system, and a spectrophotometric pH analyzer. These CO2 parameters are used for biological activity researches in aquatic environments and for climate change related researches. So our users are mainly researchers all around the world. First, a little bit scientific background. Okay, I can get the pointer started. So the CO2 concentration in the atmosphere has been relatively steadily fluctuating between 190 ppm and 280 ppm in the past 2 million years, although this figure only goes back to 400,000 years. And see this inset, the concentration has been stable all the way down to 1760 when the Industrial Revolution started. And then the CO2 has dramatically increased to over 410 ppm today. And this is all due to anthropogenic activities. Well, we have the ocean to take up a lot of this CO2 that alleviates the CO2 level increase in the atmosphere. But this causes ocean acidification, which negatively impacts coral and shellfish growth, as well as the health of the entire ecosystem. And when CO2 dissolves in water, it becomes carbonic acid in a series of reactions in which bicarbonate and carbonate ions form. Then there are 4 parameters to measure in the CO2 system, and we have instruments to measure each of them. And the parameters are partial pressure of CO2 dissolved in water, pH, dissolved inorganic carbon or DIC, and total alkalinity. Today, we'll just focus on these 2 that are realized by taking CO2 measurements. The pCO2 system measures the carbon dioxide that dissolves in the water sample by measuring the CO2 concentration in the air that's equilibrated with the water sample. And the DIC analyzer uses phosphoric acid to convert all the carbonate and bicarbonate to CO2, and then extracts everything with a carrier gas. In both cases, our equipment processes the water sample to extract the CO2 and send the gas sample to LI-COR analyzers to get the CO2 concentration readings. First, the DIC analyzer. What's shown here is our Model C6 with LI-7815 on the outside. And this model can also be equipped with a an LI-850, and I'll talk about that in a minute. With this model, we can provide a precision better than 0.1%, or about 2 micromoles per liter for a typical seawater with a DIC level around 2000 micromoles per liter. And what you see here is a multi-sampler. There's a 12-port valve here. 1 port is dedicated to standard, and 8 ports are for samples. The sample volume is between 1 and 4 mils for each repeat, and this number can be changed by the user. One advantage of this whole setup is that it only needs one standard solution. And the 3 different volumes of the same standard and 8 samples are fully automated. And each repeat takes about 3 to 4 minutes. This is the Model C5. It has the same case, but LI-850 is small enough to fit on the inside. This is a view from the side. So the 850 is right over there. With this model, it's more compact and it costs less. The precision-wise, we can provide 0.15% or about 3 micromoles per liter for a typical seawater. And for freshwater samples with DIC level around 130 micromoles per liter, we can provide a precision better than 0.5%. This is a screenshot of the program. As I said just now, sample volume can be changed by the user, but we also give you the flexibility to change many other parameters so that you can fine-tune your instrument to better suit your samples. What's shown here is the wait period between each repeat, each sample. You can control the acid volumes, how fast you inject everything, and when you consider a repeat to be good enough to finish. Also, usually we do 3 repeats out of a maximum of 5. Again, you can change that if you only want 2 repeats that are close enough. And you can change the volume of the standard here. And you can choose whether you want a best fit line or broken lines when you deal with the standard curve, which I will talk in a minute. And that's the plot area. Earlier, I said we use a carrier gas to extract all the CO2 from the water sample. So as the carrier gas flows through this, as the reaction between the phosphoric acid and the carbonate species occur, the carrier gas flows through the system. And we constantly measure the CO2 concentration in that carrier gas. So we get an initial baseline, this peak, and a final baseline. After we get this integration curve, we use the area underneath this curve as a measure of the total amount of carbon. So with that, we can use a smaller volume of the same standard in place of a second standard with a lower concentration. In this plot, we have 3 volumes at 0.8 mils, 1 mil, and 1.2 mils that represent 3 standards at 1600, 2000, and 2400 micromoles per liter. And with this standard curve, like I said just now, you can get a best fit line, which is also shown here with a very good R² value. Or if you want, you can use the broken line between 2 adjacent volumes to calculate the DIC of the standard. The DIC of the sample. So for the sake of simplicity, I'll refer to this as the standard curve. Then this is the data table in the software. We record sample ID, port assignment, volume of the sample, start time, and how many attempts there were for you to identify the sample. And these columns are parameters of the measurements. They also help us to monitor how well the instrument works. And this section would be the result. We report the integration area of each repeat as well as the average of those 3 repeats that are close to each other. This column displays the DIC. We input 2000 as the concentration of the standard for this example. And these numbers were calculated for each sample based on its average area, as well as the standard curve generated by these 3 volumes, the average area, and the input DIC concentration. The status column is color-coded. Here you can see an example whether the repeat was halted by the user, was not so close to the other repeats, they were close so they were valid, or they failed to be close to each other, or they were just analyzed so we don't know the status because more repeats of the sample are still being tested. And the pending samples are in blue, are in yellow. This screenshot was taken on a single sampler. So you'll see the port assignments will be different because everything has to go through the same, all the sample and standards have to go through the same port. Here's an example of calculating the calibrated DIC. This system with LI-7815 is very stable. So over time, it doesn't drift much. As we can see here, the area of the 3 volumes of the same standard changed only on the unit digit within about 2 hours. But if you want to correct for the drift, this example shows you how to assume that the area changes linearly with time and how to calculate a concurrent hypothetical standard curve for that sample. As you can see, the correction is very small. It's still within 0.1% as the precision we maintain. Here, I want to show you a video of the operation of the system. Turn that off. In the video, we have a single sampler. Again, all the standard and sample have to go through this same port. But the whole process is still automated. You just have to come in and change the sample. Okay, so now the underway pCO2 system. This system is used for the underway pCO2 measurements aboard a ship. And water is continuously pumped into the equilibrators. Let me turn on the pointer. Into the equilibrators while the ship is sailing. And the water is sprayed into the equilibrator through a shower head to accelerate the gas exchange between the water sample and the air inside the equilibrator. Then the air is sent to LI-7815 for CO2 readings. The system also automatically measures the atmosphere and CO2 standard gases. I don't think you can see that in this picture clearly, but there's another equilibrator behind this one. The secondary equilibrator is designed to remove the bias introduced by the atmosphere. This whole design is based on that an improved design from NOAA. The system has a rather small case and it can't be custom built. Right now, it's compatible with LI-7815, and we're working on to connect it to a LI-850. The software now allows remote control and remote data access. A 99% response time between 2 and 3 minutes, which I'll talk about more later. When I said this system can be custom built, that means these sensors are optional. Includes pH, dissolved oxygen, chlorophyll, and the GPS unit. Here are just more pictures from different angles to show you the components. This is SBE45, the selenothermograph. Water filters, there are two, one behind this one. The equilibrators, air filters, and the cooling module. This is the software. The program, the system allows you to connect 5 standard gases, but you don't have to use that many. Like in this example, if you leave it blank, this program will skip that port. This section is for UDP settings for the remote control. And this section, again, allows you to change many parameters in the measurement to better suit your project. We allow you to change how many measurements you want from each source, or how many times it repeats the air and seawater before it goes back to another group of standards. You can change how long you want to wait before each repeats of the same source, or how long you want to wait before the new source gets measured. You can also change the flow rate, and when you consider a standard gas to be stable enough. This is the data table in the program. Here we report time in UTC, the coordinates from the GPS, and the readings from LI-7815 and all other probes that's not shown in this view. In this example, we have 2 standards, the air and seawater, according to the number I showed you in the previous slide. These are the plots. We give you 3 different plots. You can plot the historical data files here. You just have to select the data file first, which are named by the date and time it was started. Then you choose the different parameters to plot. So you can choose the same data file with different parameters like what I do here, or you can compare the same parameters from different files. This is the data table for export. The selected parameters are highlighted here, so it will be easier for you. And the file will be exported in a CSV file, comma separated value. Here's are the results for the response time test. It was done with seawater and a tap water sample with different CO2 concentrations. Once we get a stable reading for the sample at around 300, we switch the water inlet to the other water body and see how fast the CO2 reading changes. And a 99% response time means the concentration changes for 99% of the difference between these 2 steady values. With that, we got a 99% response time between 2 and 3 minutes, and 95% response time around 2 minutes. A 90% response time would be between 1 and 2 minutes. That's all I have for the analyzers. This map shows where our current customers are located. As you can see, they are all around the world, in all over Americas, Europe, Middle East, and the Asia Pacific. We currently have 3 distributors in China, Italy, and Russia. So if you or your colleagues are from those countries, you need to contact them. Otherwise, I think most of you are from the US or other countries. In that case, you need to contact us directly. With that, I want to thank you for your attention, and I can take questions now.